Hello, everyone. Welcome back. Thanks for sticking with this set of videos. I'm Mike Muller from Rutgers University, and this is part 2 of process heating. Now that we've covered the basics of heating in our last episode, we'll move on to trying to contain your heat and reusing the waste heat. Now that you're heating stuff, one of the basic categories we look at is heat containment. How do you keep it where it's supposed to be and keep it from going where it's not? A lot of our factories today are cooled for environmental reasons. People work there so you cool it. If you have a hot process, you can get a double whammy where you're losing heat out of the heating system and it's going into the cooling space. The first and most obvious thing to look at is insulation. But where? Every place you're heating with process heating, you're trying to separate the process heat from the environment around it. Most insulation systems are going to reduce unwanted heat transfer by usually around 90%. We look for any bare surface and argue that insulation is mandatory. Now, thermal imaging cameras are becoming fairly inexpensive, and they can provide you with a temperature on the surfaces of piping or an oven, and will show you right where the maintenance problems are. Although not officially advised, I tend to reach my hand out and touch surfaces that seem warm or hot. If I can put my hand on a surface and keep it there, generally it will not pay to insulate it. If it's just warm, not hot, installing insulation will have a very long payback period. Commonly, advice is given to always add more insulation. You've got 2 inches of insulation, you should add another couple, but we don't find that very economic very often. Insulating insulation is not defendable, in my experience. Finally, you keep your insulation repaired. If you insulate things, then get wet, it's actually worse than no insulation at all. The idea behind that is that the water wicks out to the surface of the insulation, and it's as if the pipe has a greater surface area, and therefore the losses are greater. Sometimes more important than insulation is looking for where air or combustion products may be leaking through cracks, fittings, gaps, or openings where products come in and out. Those furnace openings can be minimized or closed when not needed. Again, you can use your infrared camera to look at these hot spots as shown in this figure. It's often difficult to measure the amount of infiltration going into a furnace or oven, but if you use a little smoke generator, like what's shown in this picture, you can at least get an idea of which direction the flow is going. There are multiple access points which can be used for sensors or measuring devices, although some of these are just for material loading or viewports. These are openings that exist, but they don't always have to be open. One of the things we look for is if your coverings on furnaces are just removed for the convenience of the operators. This includes lids on vats and doors on furnaces. And one easy fix you can do is to simply put an alarm on these things. So if you open a door or a lid to a vat and it's open for more than 10 minutes, say, a light starts blinking, something like that. Doesn't have to be too disruptive, but just a reminder. Now, if you're unable to close off a furnace, but you can still see that red hot material inside, you can often put up a radiation shield. A radiation shield is a temporary device that will reflect heat back into the furnace. Sounds good to me. These are being made with much more flexible materials these days, so they don't get in the way when you need to get access to the furnace. Now, I want to mention 2 more important points. In a lot of open baths, you're going to have heat transfer. So they're going to be hot and you're going to lose energy to the atmosphere by both heat and evaporation. One solution that's available, depending on what material you have in the open bath, is to put in these round balls. These balls will easily move out of the way if you put anything in or out, but otherwise they sit there and act as insulation. And you can see it done on a very large scale or on a very smaller scale as well. The final area for process heating where we spend a lot of our time is on waste heat recovery. If you have combustion with exhaust coming out, there could be a lot of heat that you're just throwing away. And that's something we love to use. And we may even devote an entire video to waste heat recovery later in this series because it tends to be more complicated than some of the previous mentioned topics. but boy, it can save a lot of money. One of the terms that is often used when talking about waste heat is the quality of the waste heat. Remember, if I have a river of warm air with massive amounts of air leaving, the amount of energy that's being carried out with that warm air might be huge. But because the temperature isn't that high, it becomes more difficult to use. So the two parameters that determine the amount of energy you're losing are the flow rate and the temperature. Higher temperatures are going to be easier to use, but lower temperatures are more common. Therefore, the quality of waste heat has to do with how high its temperature is, which will dictate how you can use it. While being a little bit arbitrary, there are some classifications that describe the quality of waste heat. High quality waste heat is considered anything over 1,000 degrees Fahrenheit. You can get that quality of waste heat off of systems such as power equipment, melting, kilns, incinerators, and especially thermal oxidizers. Thermal oxidizers are part of an exhaust system that destroy chemicals coming out of, let's say, a printing process and have some of the hottest temperatures I've ever seen. There's a fun story where we stuck a thermocouple into a thermal oxidizer port and it came back melted. So we just put down, instead of a quantity of temperature, we wrote wicked hot, and that has become a technical term in my shop. A medium quality range is considered 400 to 1,000 degrees Fahrenheit. Some exhausts from engines will be that hot, and heat treating furnaces and higher temperature ovens all fall within that range. Usually these are very useful waste streams, and it almost always pays back to take advantage of them. Finally, you have low quality waste heat. That includes anything from just a little bit above ambient up to about 400 degrees. Cooling water from heated equipment, output from drying processes, and building exhaust are all examples of low quality waste heat. There's no shortage of these sources. The problem is it's very difficult to utilize and get some of that energy back for other things. One of the first things you look at in a factory is any exhaust stacks associated with heating processes. These are normally a source of significant waste heat. This includes boilers, process heaters, and anything with combustion. If the temperature is above 250 degrees Fahrenheit, you can get some useful heat back from that source. And if it's above 600 degrees, you pay very quick attention and say, anybody can use 600 degrees waste heat. So we have a few things you can do with that waste heat. Since the air is being brought in to oxidize the fuel, you can preheat the combustion air. You could preheat the fuel, or you could preheat the product. Or in fact, you could simply make electricity using heat engines in some cases. When taking energy from an exhaust stack, there are limits. You really need to keep that stack temperature high enough so that you don't get condensation inside the stack, which can mix with acids in the flue gas and start to eat away your flue or other parts of your furnace system. So you have to look at what the dew point is in the stack based on the fuels being used and keep well above that. But other than that, we can use either a regenerator or a recuperator. The simplest solution may be to preheat the air before combustion. We put the air intake through a heat exchanger that interacts with the exhaust and raises its temperature. By it, I mean the intake air. It's a very easy way to save a few dollars. Now, in that example, it was an air to flue gas heat exchanger, meaning a gas to gas heat exchanger, but that's not always available or advisable. In a lot of cases, what we're going to see is that intermediate mediums are used. Pictured here is something called Dowther, which is a heat transfer liquid and is often used as an intermediate medium because of a high boiling point. What you can do is use it as a liquid, heat it up in the stack, and then take it to preheat your combustion air or whatever else you're going to do with it. So a gas-to-gas heat exchanger is not required. Now, preheating the combustion air is a very common way to use waste heat from a furnace, but another way that I'm particularly fond of is preheating the charges which are going into the furnace. It's a terrific use of low quality waste heat. You can even use combustion products. It doesn't matter, The charge that's going into the furnace doesn't care about that. What we tend to recommend is a staging hut for a waiting charge. By charge, I mean the pre-melted product going into a furnace. Shown here is a case with ingots that are going to go into the furnace and are set on top to preheat before going in. Without this step, the heat coming off the heater would be just wasted. At the risk of getting too technical for a 101 presentation, it's important to realize that when you're heating a metal and you want to melt the metal from solid to liquid, it doesn't take all that much energy to change its phase. Most of the energy is there to change its temperature. In this particular table, you see that of the 455 BTUs per pound it takes to fully melt a pound of aluminum, it takes 255 BTUs to get it to melting, and then 170 to do the melting, and then another 30 to hold temperature. So the melting is less than half. Now, if you look at water, for example, the latent heat of taking water from liquid to vapor, i.e. the energy needed to get that phase change, would dwarf the other heat transfers, and therefore you would not find a whole lot of reason to preheat water. It's done, it's just not as viable or valuable. With metals, it's a much more valuable process. Now, what do you do with these low quality waste heat streams that you get? You can use them for, as we just showed, heating liquids. You can help space heating needs. We see low quality waste heat coming off an air compressor, for example, and it's often used to support space heating in a building. Also, keep in mind that there are ways to use low quality waste heat to generate power using something called an organic Rankine cycle. By essentially using a refrigerant as opposed to water as your working fluid, you can lower the temperatures. And there are a number of devices out there that if you can get that low quality waste heat to them, you can make some electricity out of it. It'll be low efficient, but better than throwing heat away. Well, that's about as quick as I can make a discussion of process heating. It's obviously a much more complicated technology, and the fixes are complicated, but the payoffs can be quite large. We find that factories with a lot of fossil fuel waste heat opportunities, in many cases, have not really taken advantage of them. I want to bring to your attention a couple of resources if you want anything further. One is an old source book from the US DOE, which, like us, is at the 101 stage. The other is a free trade mag called Process Heating, where you get it once a month, and it would have some ideas for you, and it would essentially keep your mind focused on process heating. Thanks for listening into our process heating episodes. Next time, we'll be discussing steam and opportunities associated with steam in manufacturing plants. I look forward to seeing you next time and continuing our chat.